Next, we're going to introduce how to evaluate a given system's frequency response. Here is the definition for the frequency response. So we basically have two ways to evaluate a given system's frequency response. The first is we try to use the Fourier transform of the system's impulse response to get system's frequency response. And here's the way we do it. But here's a limitation that only for a stable continuous time LTI system we can have the Fourier transform. Here's one example. We have a continuous time LTI system whose impulse response is given there. And what is the system's frequency response? That is pretty straightforward. We can use Fourier transform. And this is the system's frequency response. The second way is if we have a system described by the differential equation, then we are able to use the Fourier transform of the differential equation to get the system's frequency response. This is how we're going to do it. We convert it from time domain to the frequency domain, and then by definition we can get the system's frequency response. Here's one example. We have a system given here using differential equation. Then what is the system's frequency response? We can convert it from the time domain to the frequency domain and then rearrange the terms. And these will be the system's frequency response. And we can get the plot of the amplitude part, the amplitude response. From the amplitude response, we can clearly see that the system is a band-stop system, and the central frequency is omega sub none, while the 3D bandwidth is f sub omega. For circuit analysis, we can also try to convert the system from time domain to frequency domain. For example, here is the capacitor. This is the description for that component in the time domain, and we can convert it into the frequency domain. Similarly, for a conductor, we can do the same thing, convert it from the time domain to the frequency domain. And here's one example. In the RC circuits, here the voltage and the output is marked in the plot. And if we know that the initial state is 0, what is the system's frequency response and the impulse response? So what we can do is we try to convert the circuit from the time domain to the frequency domain. And it is pretty straightforward. We can get the system's frequency response using the definition and plug in the parameters, rewrite it, we get the system's frequency response. And if we do the inverse Fourier transform, then the impulse response can be obtained. Again, here is the amplitude and the phase response of the given circuit. It is a low-pass filter because as the frequency increases, the amplitude response is decreasing. Also, we can identify the system's 3 dB cutoff frequency on the plot. To summarize, there are basically two ways to help us determine the system's frequency response. One is we do the Fourier transform for the system's impulse response. And the second is based on the differential equation. that can be used to describe any LTI system in the continuous time domain. We can convert them into the frequency domain and then using the definition to get the system's frequency response. Thank you.